Welcome to another video. Our previous video derived the formula that can be used to invert our model so that we can understand the conditional value function differences directly using choice probabilities estimated from the data. We did a fair amount of algebra and relying on the type 1 extreme value assumption to greatly simplify the formula for what this mapping looks like. And today we'll go a bit further into this idea and also briefly go through the empirical example that the Hotz-Miller paper covers, which has to do with fertility decisions. Again, this is the cover page or the title page of that famous paper. And just to kind of review from our last video, the proposition is that there's an invertible mapping, which they denote as psi, that maps the choice probabilities from our data to our difference conditional value functions, which are objects of our structural model. So as I mentioned, we can get these choice probabilities from the data, but we still need additional information in order to utilize them in our estimation. So first we need the formula for the mapping. For the type 1 extreme value case, we showed that that was just the differenced log probabilities for the two options in question. We also need to calculate the expectation of those epsilons in the Emax term. And then we also need to figure out how to unravel this recursive structure to our problem. So if we can handle all of those, then we'll be able to quite simply implement this approach. So let's add a little more realism to the problem by looking at a binary choice with x's that are stochastic. And for the sake of example, we'll assume that option 0 is a terminal option, meaning that once I choose option 0, there are no more choices to be made. So in this setting, how can we simplify our conditional value function for v1? Let's start by reminding ourselves what the formula for v1t looks like. v1t takes in the current states xt, and one component of v1t is the current period flow utility at those states, and the other component is the discounted expected future value based on the states today and how they're going to evolve in the future. And here the expectation is over the future states with the transition probabilities and the Markov assumption that we talked about in our last mini-series on dynamic models. And this big V t plus 1, as we talked about in an earlier video in this series, is the Emax of those over those epsilons. So we have our future value over both the future states and the future epsilons. Using the formula that I just showed you, we can rewrite big V as being equal to little v0 plus the Emax of epsilon 0 and epsilon 1 plus the inverted choice probabilities. Everything else in the formula is the same. And so the trick that we can implement is that we can, if choice 0 is a terminal choice, then it's not going to have a future value component, because once I choose option 0, I'm done making choices. So I can just have this v0t plus 1 just be a function of xt plus 1 times alpha 0. And then I don't need to do backwards recursion. And then the only thing left is this Emax term over these epsilons that I need to worry about. So if we have type 1 extreme value errors, it can be shown that this Emax formula is just minus log p0 plus Euler's constant, where p0 is evaluated at the xt plus 1 states. And indeed, we showed this in a prior video that big V was equal to little v minus log of p0, or little v0 minus log of p0. So that's where I'm getting that from, was the algebraic manipulation that we went through in the prior video. This is just a different way of writing out that same exact thing. So how is this? Well, I just kind of walked through that a second ago. As long as the epsilons are type 1 extreme value, then we'll get this formula here. So we can plug this into our final equation, and then we just get that little v is equal to little u plus beta times the expected value over the x t plus 1s of little v0 t plus 1 minus log p0 t plus 1 plus Euler's constant times the discount factor. And so then once we apply the fact that choice 0 is terminal, then this thing just becomes xt plus 1 times alpha 0. And then this whole right-hand side has no dynamic component to it. And so then we can greatly simplify our estimation. So there's no recursion over the big Vt plus 2 because little v0t plus 1 is linear in parameters. So then we can estimate the P0 of xt plus 1 term using our data, and we could do this with a non-parametric bin estimator or other options. This is going to be similar in principle to how we estimate the transition probabilities in a first stage. And so basically, we have a simple static logit model with an adjustment term for this log of P0. So in stage 1, we're going to estimate the CCPs, the log of P0, and the transition probabilities in the Fs. And we can use bin estimators for both of these, or we could be a little bit more parametric. It's not a problem. And then in stage 2, we can estimate our structural utility parameters using a simple logit model where we've added another regressor to our model that captures this adjustment term that is a function of the P's and the F's from the first stage. So what do Hotz-Miller do in their paper? Well, they're looking at couples' fertility and sterilization decisions. So in this model, the terminal option is to become infertile through sterilization. And in their paper, the state variables are the number of children in the family, how old the wife is, and how educated the wife is. And the choices are sterilization or not. So this terminal option, this option 0 that we've been talking about, is the sterilization option. And it's terminal, and so there's no more fertility decisions after that option has been selected. And then there's also transitions on the HT variable, right? If I don't sterilize, then there's some probability that I'll have a child in the next period. So my HT plus 1 will maybe go up by 1 in the number of children entry with probability alpha. So I have some state evolution of what's, if I choose to not sterilize, if I choose option 1 in period t, then my HT plus 1 is going to evolve according to this formula, where these are indicator functions. And so that's the gist of the Hotz-Miller approach. And this was a very influential paper that has many, many citations on Google Scholar and has further been remixed in subsequent research that we'll talk about in later videos in this mini-series. So we've gone through an example about how these conditional choice probabilities can simplify the estimation in a model where we have a terminal option. But what if we don't have a terminal option? Can we still use this method? The answer is yes, and we'll go through that in our next video.